Hello everyone. So today we're going to start off the next section of our course on chemical reactivity, where we are going to talk about how molecules collide and rearrange to form new molecules, the speed at which they do it, and how much of that is formed. So we're going to do this by talking about energetics and specifically potential energy surfaces. So what I have shown here is an example of a potential energy surface. You can see everything that we consider when we're thinking about how molecules react in terms of their minima, Valley Ridge inflection points, which we won't get to in this course, but they do exist, transition state structures, minimas, and you'll notice on this path that there are many different paths a reaction can take, right? So you can think about this, well, this three-dimensional map looks a little convoluted, and when you think about molecules, you're again thinking about things that you haven't necessarily seen yet. It might be better to think about it more like hiking, right? Because that's something hopefully most of you experience. When you're going from one point on a hike to another, you're typically going to be trying to find the lowest energy path to get there, right? So you're not going to be walking to the very top of the mountain, unless that was your goal, but molecules aren't looking to do that. Typically, you're going to be looking to go through a valley and over the lowest point between two mountains to get to the next area of interest, right? So you're looking for the lowest energy path to get there. And that's what molecules are doing. So they're going to look for the lowest energy path and take that more often than they do the higher energy paths. All right, so we are going to look more closely at potential energy surfaces. We'll zoom in on the one we have here. So again, keep in mind that we're talking about energy going up. And the things that we are going to be most concerned with are the minima and our transition states. So notice here that we have two possible transition states. We have a minima for product A, a minima for product B, and our reactant. So there are many different ways that this reaction could go. In this case, there are two shown that have the lowest energy path to the two minima that we see. So this is a fairly complex thing to draw, and if we're just trying to draw out a reaction or an idea of what we want to see happen, we're going to take a single line. And in this case, we would represent that by one of these red lines, or I'll draw over it in a very thick purple line. We'll take that line there, and we'll draw that onto something a little simpler. We've seen these before, so hopefully this is nothing new to you, but we're going to introduce this now. Instead of in conformational analysis, we're going to talk about potential energy surfaces in terms of reactions. So we have our energy increasing, we have our reactants. Let's say we're doing reaction going from our reactant to product A, and this would represent the purple line here. So here we're talking about just the lowest energy path, not all of the other paths around that. So this is a much simpler picture of talking about the transition between one reactant and the product. We can also convey these in terms of a reaction. So let's take, for example, the reaction of A plus B, and that's going to, we'll call it AB. Nothing too creative here. We draw this on a potential energy surface. Again, we're good organic chemists, so we label our axes. We would start with A and B, going to A, B. And at this point right up here, that we would define as the transition state. So the highest energy point where A and B are coming together to form a new bond. So this we refer to as our transition state, and often you'll see that designated by a double dagger as drawn there. So and again, it's the state in which it transitions from two reactants towards products. Right? And then these would be our minima. So the key energies that we're going to talk about here are the energy between the products and the reactants. That's going to be delta G. We're also going to look at the energetics between the reactants and our transition state, and we'll call that delta G double dagger. So we're going to talk about energies in terms of Gibbs free energies because they describe the system most fully. So delta G double dagger will refer to the amount of energy required to overcome the barrier of forming the bond. So this will be relating to kinetics. Or the speed of our reaction. Whereas delta G for the reaction will give us the thermodynamics. Or the ratios of products and reactants. So one will tell us how fast we're going to make the products. The other will tell us how much of the product to expect once equilibrium is hit. Right? So we're going to talk a lot about delta G's because really these are the driving force for all for all reactions, right? We're trying to lower the free energy of the system. So let's go back real quick and review delta G's just a little so that we can get into talking about what makes reactions tick, right? What are the driving forces for reactions occurring? So delta G, hopefully you guys remember Gibbs free energies are defined by the enthalpy, delta H, minus the temperature times the change in entropy or disorder, right? So if you aren't comfortable with these, please go back and look them up. We'll go through them pretty quickly here. So we're going to quickly talk about enthalpy first, delta H. This is the energy associated with bond breaking and bond making. Ooh, that's not great. All right. So it's key to keep in mind that when you're forming new bonds, you're releasing energy, and you have to put energy into a bond to break it. But we'll talk about that amount of energy later. But hopefully you guys remember seeing this diagram, right? Talking about two atoms coming together to form a new bond. As their orbitals start to interact, you decrease the energy, you make it something more stable, releasing energy into the system. So how do we calculate delta H? Well, we can do this by looking at bond breaking and bond making. And when we do that, we're going to talk about specific types of bond breaking. So there are two classes of bond breaking that we're going to deal with in this course, and I'll quickly just introduce them now. There's homolytic breaking. That's where you have a bond between X and Y, and you break that bond by giving one electron to X and one electron to Y to form what are known as radicals. So these are referred to as radicals. We'll get to these in a few days. You'll notice that the arrow here has a slight difference from our two full-headed arrow. This is a 1 electron arrow, whereas the one that we typically drew when dealing with resonance so far is a 2 electron arrow. This is also referred to as the fishhook arrow. Right? So homolytic breaking is one form. The other that we'll see later on is giving 2 electrons to one atom. This is heterolytic breaking. So you're breaking the bond heterolytically, so unevenly. This we will get to in reactions later. Homolytic breaking is what we're going to focus on when we're dealing with delta H's. So I'll erase that for now. It's just kind of good to know. So calculating delta H. Is going to be the energy of bonds broken minus energies of bonds formed. If you can't remember it's alphabetical, broken before formed. This is all in table 6.1 in Klein. So again, you're not expected to be able to memorize these energies. You just need to know how to use them. You'll be provided with any energies you need on exams. So let's look at an example of calculating delta H. Here's our reaction. And if we go to the table in the book, so let's first identify what's happening in this reaction. You'll notice here that we have replaced the CF bond. So it's probably good to keep track. You're making a CO bond. Now notice that we are also making an HF bond and breaking an OH bond. So those are the 4 energies we're going to need. We can get those from the book. 448 kilojoules per mole for the CF bond. So looking at that bond right there. Looking at the OH bond, 498 kilojoules per mole. Now if we look at our OH bond, our CO bond, we're going to see that we have 381 kilojoules per mole. And then our HF bond, we'll do it in a funky color just for fun, will be 569 kilojoules per mole. All right, so now we have all of that. We can come down and calculate our delta H, which would be 448 plus 498 minus 381 plus 569. And from that, we get delta H is negative 4 kilojoules per mole. Okay, so what does that number mean and what does it represent on our potential energy surface? So that's how we calculate it. So let's look at what that number actually means. Right, so using the same reaction, we can take this and draw it on a potential energy surface. So here we have our reactants, some barrier, and our products. So you'll notice that I've drawn the products lower in energy. That's because we have our delta H here, which indicates that the products are lower in energy by 4 kilojoules per mole relative to the reactants. Right, so another thing to keep in mind, just as a quick note, you'll notice that all of the atoms are accounted for on both sides of the reactions. On a potential energy surface, you need to keep track of all of your atoms and electrons because they should all be accounted for in order to calculate the delta H's. All right, so we can define this reaction as being product favored. Or exothermic, meaning that it gives off heat. Right? So hopefully that is familiar to you. We'll do one more example real quick, just so you guys see the opposite of this. So if we have a reaction where we're mixing methane and water, to attempt to form methanol and hydrogen gas. Well, I've drawn it out here so that you see which bonds are being made and broken. So we'll go red, broken, blue, made. We can go to our table 6.1 in the book and find the energies. 435 kilojoules per mole, 498 kilojoules per mole, 381 kilojoules per mole. I know this is exciting. 435 kilojoules per mole. So we get that delta H is 117 kilojoules per mole. All right, so notice that in this case, this is a positive number. If we come to our potential energy surface here, we would see that if we take our methane and water, we're going to make methanol and hydrogen gas, but they are going to be much higher in energy. So here, we would say that this is a non-spontaneous reaction. So these aren't just going to turn into methanol and hydrogen gas when you mix methane and water. So it would be a reactant favored and also endothermic. So we can use both of these terms to refer to this, which means that it would require heat. You often hear about this in first year as heat as a reagent. All right, so there are the two cases. You have exothermic, which is a spontaneous process that gives off heat, or an endothermic process, which will require heat and will not be spontaneous. So the next one that we are going to look at is the other form of energy that we need to consider in looking at Gibbs free energy, and that is entropy. So most of the time we're going to focus on delta H because delta H is easier to quantify than delta S. There are some ways of doing it, but it's really, measuring disorder is a difficult thing to do. So really, it comes down to more molecules equals more disorder, because there are more ways to organize the system. So, oh, well, that is a very disordered molecule, but let's do it in black. An example, we could look at the cyclization process. Which would be negative 13 joules per Kelvin mole. This would decrease the disorder in the system, but it's really a hard thing to quantify. So in general, we'd say that delta H generally trends pretty heavily with delta G. So if we come back up here and just look at delta G really quickly, you can see, well, maybe I should have just redrawn this. Yeah, here we go. Delta G is directly related to delta H. It's also directly related to delta S, but it also has a scaling factor of temperature. So delta H is often thought to be a better predictor of delta G's, and we often use it as a predictor of delta G's just because it's easier to do that. All right, so again, delta G tells you about the equilibrium of the reaction. Whether or not it's going to be reactant favored or product favored. Right, so if we have A plus B, well, I'm doing some fun things tonight. A plus B goes to C. We can define this in terms of an equilibrium, and we can actually predict which one we're going to make more of based on the relative delta H's. But we can also measure the delta G of the reaction because these are all physical observables. This is really the power of Gibbs free energies, is that you can take things that are physically measurable, like concentrations of reactants and concentrations of products. Right? We've just talked about all of the methods that you can use to identify molecules, such as mass spec, IR, and NMR. And you can quantify these things. So we can take delta G's, which we defined as and use another equation. So we defined it as delta H minus T delta S. We can take another equation and put that in terms of physical observables, because KEQ is equal to the concentration of products over reactants. So here, you can measure your concentrations and from that get energies for your reaction, which allows you to develop trends. It allows you to make predictive models for new reactions. All right, so that's the power of Gibbs-free energies. If you have any questions on any of this, please go back to first year, or we can talk about it in office hours. And our next video will be on, oh my goodness, our next video will be on kinetics, where we talk about how much energy it requires to go over or to meet the transition state. Okay, have a good night, guys.